Hi, welcome to my channel JaberTime, where I do math videos with simplified examples from algebra to calculus and differential equations. This is my second video today for calculus 3, which I just started today, and hopefully that's the plan. By the end of this semester I'll have all calculus 3 vector calculus up there. I'm also working at the same time on college algebra, which I'm going to be recording also after this video. So if you're here for the first time and you like this video, hit the like button, subscribe if you like it, and hope to see you again and again. Thank you, and let's get into it. We're going to talk about vectors. As you could see from this screen, I have the subtraction of u minus v as vectors and the addition. This is something that I want you to pay attention to. In short, the addition of two vectors starting at the same point will be the diagonal in a parallelogram that you could extend and complete, where the subtraction u minus v is actually a triangle look connecting the endpoints of v and u, but pointing to u. It's kind of funny when I say it pointing to you, but it's all about you, by the way. So u minus v will be the vector that completes the triangle pointing to you, not to me. If you want to go v minus u, you have to go this way and point to v. Just pay attention to that and think about the sum is inside as a diagonal, and the difference is just like completing the triangle. Anyway, as you can see, I do the graphs ahead of time. Imagine if I do this while I'm recording and you're watching me. That's not too bad, but the disadvantage, the way I see it, is I will be covering less and less math for you. I want to cover more. So my videos are lectures with examples. I take my time graphing them. I take my time writing my notes. I take my time cleaning up my notes and scanning them, and whatever comes after. This way I could record and cover more math for you, and without going off topic like I just did about pointing to you and so on. So I'll try to focus with you guys, and if you like this video, please help me by subscribing and hitting the like button, and that's how my channel will grow. I am so committed to my math videos. I've started teaching in 1987, and I have so much math background and too many files and too many file cabinets that I would like to clean up and convert them to YouTube videos simplified with examples, all the way from algebra to calculus and differential equations. And I'll be going back and adding more videos. I will be calling them part 2 and part 3 and so on. I will be adding playlists of math riddles and math activities. So stay with me and you'll see more and more coming. Every video, every week, pretty much I have at least 1 or 2 videos. I can't be committed to some specific days, but they are coming. So if you are one of my students, I want you just to understand that and be patient with me, but you're gonna have them, trust me. It's a commitment and I'm working on it. Okay, let's get into it and stick to the subject here, which is vectors, and I have a lot of slides, so let me move on and show you. Suppose a particle moves along a line segment from point A to point B. The corresponding displacement vector v has initial point A, it's called the tail, and has the terminal point B, called the tip. And we indicate this by writing v as a vector symbol on top of the points A and B. A is the start and B is the end. Tail, tip, start, end. I have another graph here with different color. As you could see, it's called U. Now me, one more time. Notice that the vector U, which is CD, from C to D, has the same length and the same direction. Same angle, if you want to call it angle-wise, right? As V, even though it is in a different position, place, in other words. We say that U and V, you and me, are equivalent or equal, and write U equals V. I think that's good enough, guys. Let's move on. So the zero vector, also as a comment, without forgetting that, because we do have a zero vector, which is interesting, has length of 0. It is the only vector with no specific direction. Hard to imagine, right? Okay. Combining vectors. I mentioned that on the first slide as an introduction, so let's see how we could handle this. Suppose a particle moves from point A to point B, so its displacement vector is AB. Then the particle changes direction and moves from point B to point C with displacement vector BC. So the particle is moving this way, then this way. As you could see, AC is a little bit darker color, like red on top of black, because that's my main part. The combined effect of these displacement is that the particle has moved from point A to point C. So the net, or the result, is the point actually moved from point A to point C. First they went this way, then they went this way. That's called the displacement. The resulting displacement vector AC is called the sum of the vectors AB and BC. And we write AC as the sum of AB and BC. Now, on the first slide, I showed you the graph of the sum as a diagonal. In this case, I showed it to you as, I'm showing it to you as a triangle. But it's simple to remember as a triangle. It's like you go this way, then you go this way. I would call this one shortcut. Pretty much. It's not confusing, so you could do it. The vector addition, which is a triangle law. First, second, the sum will be right there. As simple as that. That's what they call the triangle law. If U and V are vectors positioned so that the initial point of V is the terminal point of U, the initial point of V is the terminal point of U, which is common sense. You end up here, so this is your start point for the coming vector after, which is V. Then the sum U plus V, as you add them, will be the net right here. Is the vector from the initial point all the way, initial point from U, to the terminal point of V all the way up here. Next. Now, as you could see, the parallelogram given to me. And you don't see it as the main diagonal as I graphed it earlier, but I'll show you. If we draw another copy of V, this right here, we make a copy right there with the same initial point as U. So I put it where U started, okay? Completing the parallelogram, as you could see right here, we see that U plus V equals V plus U, okay? In green, that was U plus V, so it gave me U plus V, which is up here. Now, if you copy this right there, and then you copy this up there, so you're using the blue graph. Now it's V plus U, took you from the first start point till the last end point. As you can see, it's the same vector. Okay, so what this says that the green equals the blue, or U plus V is the same thing as V plus U. This gives another way to construct the sum. This is how we saw it earlier. If we place U and V so they start at the same point, instead of having U here and V here, I move the V down there. This is dashed now to stay focused. And earlier this was the sum. But if you see it this way, it's a diagonal of a parallelogram starting from the same start point. This is called the parallelogram law. Definition of a scalar multiplication. If C is a scalar, a constant, and V is a vector, then the scalar multiple C times V is the vector length, is the vector whose length, is the absolute value of C times the length of V. And whose direction is the same as V. Now, if this is a little bit confusing, don't worry too much. I'll show you some graphs to show you what I mean by this. Just keep this in mind. Whose length is absolute value of C, that constant, times the length of V. Of course, if C is positive, you keep the same direction. If C is negative, you go the opposite way. If C is 0, you're killing it. You're just making the whole thing 0. Or V is 0. I mean, you don't have anything. C times V will end up 0. Okay, this is what I mean. This is V. This is 2V. 2 is positive. That's a scalar C. So you go in the same direction. And this length right here is this length times the absolute value of 2, which is 2. So it's twice the original vector V. If you go negative way, negative 1, the length of this is the absolute value of negative 1, which is 1, times the length of V, which is V. So that's what they meant. Notice, looking at these, it's the same direction, twice as much. This is half, same direction, same angle. If you go multiply by negative, you go the opposite way. Instead of going like 45, you go down the opposite way, kind of like 45 degrees from the negative x-axis. Negative 1.5 times V, 1.5 this much, half this much. It's almost like this, but the other way. They're all parallel vectors, same direction, same angle. The vector difference U minus V. That was mentioned in the first slide. And I remember when I was saying pointing to and so on, that's what we have. How do you subtract? Well, to start with, we go back to the addition, because subtraction is part of addition and division is part of multiplication. It's like two faces for the same coin. That's what we call it. So we change it to addition to the opposite of V. Let's take U step by step. I want to go U minus V. I know V, so that's V, kind of like now in pencil. This would be minus V from the previous slide. Now I'm adding U and minus V. For some reason, whenever I say U, I think about you as like my students and so on. So I'm adding U and the opposite of V. Add U and the opposite of V. One of the examples or the slides earlier, I showed you that this is the diagonal, since they have the same start point for the parallelogram that ends up being graphed. So let's move on from this graph to another one. Take a look. Now, this is V up here, and this is the sum of U and negative V, or differently, it's U minus V. Take it up here. Same direction and different position. That's equivalent. Now ignore the rest. So what do you see? I see a triangle. It says U minus V, and it's pointing to U. All right, I think that is clear. And in short, this is what we have. Here's U and V. and here's u minus v. Let's look at components. What is the components, or what do we mean by components? If we place the initial point of a vector A at the origin of a rectangular coordinate system, the one that we saw earlier in the previous video, then the terminal point of A has coordinates of the form A1, A2, or A sub 1, A sub 2. And if it's a 3-dimension, it's going to be A sub 1, A sub 2, and A sub 3. The coordinates are called the components of A, and we write the following. The vector A will be written kind of like the symbols of less than and greater than. And 3-dimension, we'll write it this way. Note, we use the notation with the kind of like less than and greater than for the ordered pair that refers to the vector. You see I'm underlining both with green to tell you that this is a vector, so as not to confuse it with the ordered pair as parentheses A1, A2. This is the point that we're looking at when we graph, thinking that this is a tip point from the origin, which is the start point or the tail. Alright, so the one here on the line with kind of like yellow, this is a point where this is referred to as a vector. Note, we can think of all of the geometric vectors as representations of the algebraic vector A1, A2. The particular representation of OP, O for the origin, P for the point that we are going to, from the origin O to the point P, A sub 1, A sub 2, is called the position vector of the point P. Given the points A and B, x1, y1, z1, x2, y2, z2, the vector A with representation AB will be this. That means you are actually moving this from this point to this point, setting it to start at the origin, because that's the end point. How far you move, right? How far you move. It's kind of hard to say right anymore because we're not in XYZ, so I'll take it back. How far you move on the X direction, how far you move on the Y direction, and how far you move in the Z direction starting from the origin. So hopefully that's clear. What is the magnitude and or length of a vector? I kind of mentioned earlier that direction, but we didn't focus much about the magnitude, which is the length, at least for now for us. The magnitude or length of a vector V is the length of any of its representations and is denoted by the symbol absolute value or double lines this way. That's magnitude or length. Pretty much a distance formula. Imagine if you have a C hypotenuse and you have the X component and I have the Y component. That's how far you go horizontally, how far you go vertically. To find the shortcut, which is sometimes called a shortcut, formally speaking, it's called hypotenuse. You just do the math as a distance formula or use Pythagoras theorem. So that's pretty much it. That would be the same for 3-dimension. If A is A1, A2, and B is B1, B2 as vectors, then the sum of this vector and this vector, all what we do is we add the components. Look, A1 added to B1, A2 added to B2, and that would go on the second place. Subtract, same concept, A1 minus B1 will go here, and A2 minus B2 will go on the second place. If you multiply the vector A by a scalar C, you just multiply inside, kind of like distributive property. Same way for 3-dimension. I don't think you expect me to read this whole thing, but Just a quick hint, if you feel like sometimes I'm going fast and you wanna stop and see it, and you know that I'm not reading it, just hit the space bar, that will stop the video. Hit the space bar again, that will play the video again. So the space bar plays as a remote control for play and pause. Okay, let's take an example. A is 4, 0, 3, and B is -2, 1, and 5. What's the length of A? And what's the sum of A and B? The difference of A and B? It's all algebra steps, so I'm not trying to take too much out of your time, so I have it all displayed for you. How do you find the length of A, or the magnitude? Take the square root of x squared, y squared, and z squared. Just do the math and apply it. That should do it. How do you add these two vectors? Well, let's add the last component. 3 and 5 will give you 8. Yes, looks right. How do you subtract? Same thing, you just subtract components. Let's go first spot first, and we'll just skip the other ones. I mean, 4 minus -2, it is 6. How do you multiply a vector by a scalar? You just multiply across, or we call it distributive. 3 times. 3 times 4, 12. 3 times 0, 0. 3 times 3, 9. Right there. Multiply b by 2. Add 3a and 2b, or 5b. Just do it. Let's do that 31. Just quick. Twice a, 5 times b. Twice a, that's a 6. 5 times 5, 25. 25 and 6, 31. All right. Okay. Let's talk about properties of vectors. If A and B and C are vectors in Vn, and B and E are scalars, this is Vn as vectors with n part inside, like n equals 2, n equals 3, that gives it like ABC and so on. I'm using different colors to distinguish because it's almost like the same size. This would be C in a vector V. Sometimes we call it V1, V2, but those are vectors, those are scalars. This is how you add. A plus B is the same as B plus C. Commutative, associative, the zero number exists, the opposite exists. Scalar multiply, that's a scalar. Two scalars multiplied, you could distribute from the right side. Two scalars multiplied together times a, you could just take it one by one, and 1 times a as a scalar 1 will keep it the same. As you can see, I don't want to read too fast or slow down, I mean. Besides, I don't want to skip them. They're right there. It's good to see them because, as I said, my videos are more like lectures with examples. They're not just examples. The standard basis vectors, which is called I, J, and K. Imagine if they change J to D. That will be I, D, K, right? Just kidding. Back to math. IJK. Sounds funny when you say IJK, but I'm used to hear IDK. Okay, back to math. And one more time. They have length of 1 unit and point in the directions of the x and the y and the z axis. This is I, this is J, and this is K. Looks like an X. It's a small font. I, J, and K. So you know which one is which, right? I for X and J for Y and K for Z. So I is 1 unit in the X direction, nothing on the Y direction, nothing in the Z direction. You're moving on X, you're not moving Y or Z, just one direction. J will be just 1 for Y and nothing for X or Z. Pretty much the same thing here, same concept. That's the same way in 2-dimension. 2-dimension we use I and j, and that refers to the point, or pointing to the point on the xy axis as 1, 0. And this j, which is 1 unit, will be pointing to the coordinate 0, 1 on the y-axis. So in 2 dimensions, we define the following. As I'm writing this down here in 2 dimension, that's pretty much it. And that is it for this slide. Let's take a look at another graph. So if you are going A much, which has components A1 and A2, so you're going A1I, because I is like telling you to the right. 1 unit is not going to make a difference on length, just like it gives a direction. So when I say 5i, I mean I'm moving 5 units towards the positive x-axis. So that's exactly what I means, all right? Same thing for j. If a equals a1, a2, then we can write a, which is a1, a2, as a1, 0, and 0, a2. Interesting, right? And simple. But that's a1 times 1. And that's a2 times 1 from this side. That's a 0, of course. 1, 0 is a short way, or represents, the short way of calling it I. It's a unit in the positive x-axis. This is a unit in the positive y-axis. There's no x. That's called j. So it's a1i plus a2j. This much and this are identical. Here's in short. That's what we have. So if you see this, you could write it this way. Of course, it's good to know both ways, especially when you solve and simplify. So using i's and j's, using those symbols will be needed as we go. 3 dimensions, same idea. Here's an example, quick. 1, -2, 6 as a vector could be written as I minus 2j plus 6k. Okay, let's move on. I still have enough slides yet, so this video is going to be longer than the first video, which is fine. But I have all the notes for you, as you could see, so let's move on. Here's an example. If a equals and b equals, which are stated, express the vector twice a plus 3b, 3 times b, using ijk. 2a plus 3b. Here's a, I took it from here. Here's b, I took it from here. Multiply a by 2, multiply b times 3. Use the distributive property. Use the distributive property. 3 times 7, for example, is 21k. 2 times -3k is -6k. Then combine the same components, or the same letters. 21k minus 6k is 15k. Same applies for the i's and j's terms. That should be a quick example, and just like algebra, as you could see, but it's good to know like how would you add and multiply scalars and videos. What's a unit vector? A unit vector is a vector whose length is just 1 unit. So the vector I is 1 unit. That's called a unit vector. If you're pointing in between x and y axis, and you want it to be 1, it's almost like you're saying a right triangle isosceles with 45 degrees. So the sides will be square root of 2, if you know what I'm talking about. But let's just, as I said, stick to the notes and stay focused. So I, j, and k are all unit vectors. In general, if a does not equal to 0, let's say the length of the vector a is 20. How do you make a length or a vector that has 20 units, make it 1. Divide by 20. So if you have $10, divide by 10. Now you have $1. Give it to 10 people equally. Each one will get $1. In general, if a does not equal to 0, we could divide the unit vector that has the same direction. It's going to keep the same direction as a is. We call it u because it starts with the letter u from the word unit. You take the vector a, you divide it, because that's like dividing, by its length. So when you have a vector that is, as I said, 10 units, and you divide the components by 10, you're actually shrinking it down to a length of 1 unit. That's another way to write it down. Let's take an example instead of just speaking formally this way. Find the unit vector in the direction of the vector 2i minus j minus 2k. Well, this is pointing somewhere, has an angle. But you could tell from it that it's not a length of 1. You're going 2 on the positive x-axis, down 1 unit on the y-axis, and actually not down. It's a habit to think x and y as y is down. You're going on the y direction to the left 1 unit, and down with the z-axis 2 units. So that's not a length of 1, it's longer than 1. First we find its length. Do the math, just the formula, which is distance formula, 3-dimension. It's 3 units. How do you shrink this down to a unit? Just divide it by 3. And how do you divide a vector by 3? It's like a scalar multiply by a 1/3. So divide every component by 3, and that should do it. That's it. That's how you do it. It's an application. Vectors are useful in many aspects of physics and engineering. This is a fact, you know, we don't do math just for fun. It's actually in the real world. It's the other way that sometimes students think when they go like, why do I need math? Well, math is out there. Everything in life speaks math. We try to make it clear so you could solve problems with rules of adding and subtracting, and we write it down in math books. So we did not create exponential functions because we want to. There's things in life that they double, and that's called exponential. So we speak math by telling you how exponential functions behave and so on. Back to the topic, applications. Vectors are useful in physics and engineering. A force is represented by a vector because it has both magnitude, and which is measured in pounds or newtons, and it has also direction. So in physics we use the word force, and that's a vector because it has both a magnitude and direction. Any vector has a length and has direction. If several forces are acting on an object, the resulting force experienced the object is the vector sum of these forces. Here's a graph. A 100-pound weight right there hangs from 2 wires as shown. Find the tensions or forces T1 and T2 in both wires and their magnitude. We first expressed T1 and T2 in terms of their horizontal and vertical components. Back to trig concepts. This is how we do it, by the way. Now, if you make the right triangle right here, you could see that T1 components wise is going left that much and going that much up. Well, this is a right triangle, and T1 is actually now negative because you're going left. The magnitude of T1 times cosine 50, because that's 50, that's 50, that should be 50 down here, alternative interior angles. In the I direction, that's X direction, and plus T1 magnitude times sine 50 opposite in the Y direction, call it J. On the T2 part, T2 will be magnitude of T2 times cosine 32 plus magnitude of T2 times sine 32. If this is too fast for you, I'll take a half a minute and show you this from trig. I'll come back to the problem. Just be with me for like kind of like half a minute. This is the right triangle, ABC. We know that cosine is adjacent over hypotenuse. If you cross multiply or multiply this way, that's C times cosine theta equals A. So what is the base or the adjacent? The adjacent is actually C multiplied by cosine theta. Same thing applies here. Cross multiply. B is C sine theta. In short, that's how we do it. So keep that in mind. Whenever you want this part, look here and take it from cosine. And if you want the opposite, look here, apply it to the sine, and you're done. Back to the problem. So we have this. Now, T1 plus T2 equals negative W, which is 100 in the direction of J. The resultant T1 plus T2 of the tensions, see this right here will be the sum, if you remember, the diagonal that completes a parallelogram and goes in the middle. That's the sum. That was in the first slide. So that is going to be, as they say right here, counterbalances the weight down here. We have 100 pounds and this is going up, or 100 pounds, yes. So that's going to be 100, but this is also, it's going to be 100. Balancing it, counterbalances it in the positive y-axis, because T1 plus T2 is this right here, pointing up in the positive y direction. That's why we call it 100J, not negative 100J. All right. Now, this is T1, this is T2. If you add them up, you go up this way, which is equivalent to what we took from here as 100 in the positive y-axis, which is J. I have this in blue and I have this in green. But if you want to compare right and left of this equal sign, the right hand side does not have an I in it. So any component right here with an I will be cancelled. The J part, only the one stays to compare right and left. The blue part is gone because that's an I part. And where the I part comes from, I have minus T1 cosine 50I minus T1 cosine 50. That's with the I part up here. And from the T2 component, I have T2 cosine 32I. Cosine 32 times T2 magnitude. After rearranging, this is the I part and this is the J part. This has an I, this has an I, this has a J, this has a J. So by adding them, I group this and I group this. To distinguish, I use two different colors right here. This whole thing is 0 and this whole green part is 100 without saying I and J. All right. Okay. Now let's use algebra skills and we'll be done with this video shortly. Rewriting them, highlighting T sub 2, that's one way to do it. You could do it some other ways, of course. Solving for T2 by itself, move this to the right side, becomes positive, and divide by cosine 32. I have T2 by itself. Take it, plug it in right here. That's called substitution method. and that's what we have. I don't have to keep it colored anymore. I just want to see what is happening. All right, now this and this talks to each other. Sine 32 over cosine 32, that's tan 32. That's tan 32. If you take T1 and T1 magnitude out as a common factor, so going from this right here to this right here, I did two things. This right here is tan 32, and this right here was pulled out as a common factor. This is what we call it two birds, one stone. Sometimes we have to, especially in higher math, we don't have enough time to simplify every single step, so sometimes we combine steps. Besides my style, if you notice from this video or the last video, I like, if I start an example, I sometimes reduce the font, as you could see, because I want to fit everything on one screen. I kind of dislike if I start right here and I end up down after enough slides. So students, when they are watching my video, they don't have to go back and forth to see what was it. Was this T1 or this one was T1 and so on. No, I'll just keep it there so you can stay focused with me. Okay, enough of that. Let's move on. We're trying to solve for T1. So divide this whole thing by this set of parentheses. And everything here with a calculator. Make sure you have to use degrees because it's in degrees. Approximate to 85.64 pound. If I have T1, I think I could go back here to the red part and find T2 because T1 is part of the game. That's what I did. So T2 magnitude is 64.91. And let's summarize this whole package because we want to make sure that to get full credit that we're answering the question the way they want it. This is a summary. So the magnitudes of the tensions are 85.64, approximate of course, and 64.91. And the tension vectors are T1, approximate to this much, I and J. I went back and wrote this because I know now what's T1, I know what's T2. Sorry, right here. Plug them in and you could end up with the decimal form for the I part and the J part. And that should do it. It's close to 40 to 45 minutes. Most of my videos are from about 25 to 40 to 45 minutes. And I'll try my best to make them less. But it's kind of hard with my style because I like to cover more math for you. Anyway, if you're up to this moment with me, that means you are watching the whole video, and I really appreciate that. And I would like you to support me by hitting the like button if you like this video, subscribe, and if you have any comments, leave them down below. And I'll see you in the next one, which is in a few days. All right. This is my second video for Calculus 3, and I will be going on and on. By the end of the semester, you're gonna have them all. All right. After this video, I'm recording college algebra, also 2 or 3 videos, depends on my time, but same day. All right. Thank you for watching, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.